Okay, sorry about the little delay. I just got back from Europe yesterday, and I'm afraid my body is still a little confused about time and whatnot. But anyway, it's later in the day for me than it normally is. So let's get started. Somebody uh, took the trouble to write me a detailed set of questions, 8 questions in fact, about the general topic of hypothesis testing and p-values and what it all means. And this is a critical point. This is not a class in mathematics. This is a class in statistics and computer coding, but that doesn't mean it's not rigorous. I want you guys to really get the point in what's going on. There's a difference between able to mathematically prove a result and really understanding it. And understanding hypothesis testing and understanding what p-values and t-values really mean is at the heart of really understanding a statistical problem. So I want to use the student's question as a framework to go over these things one more time, and hopefully you'll really get it. I always tell my friends when they say a study says this, a study says that, I always basically indicate big deal. I have zero faith that it has any real meaning, and the reason that is because I think I have a reasonable understanding of hypothesis testing. Anyway, so the first half of the class is going to be a discussion via the answer to these 8 questions of sort of my views of hypothesis testing. And then for the final part of this class, I'm going to do a reasonably systematic analysis of the flights data set. And this means I'm going to take the point of view that what can you discover from it? What kind of R do you need to put it into a usable form, and what can you get from it? But anyway, to start, 8 questions. So I was asked 8 questions, and they were as follows. What is a statistical test? What is statistical significance? What does a p-value represent? What are all the different arguments and their values based on which we accept / reject null / alternative hypothesis? Discuss all possible cases. What is a t-value? What is a p-value? How are they related? Which hypothesis should be the starting point, null or alternative? What should our orientation be for accepting or rejecting the hypothesis? What is type 1 error? And how can we compare 2 means with a t-test? Now, some of these questions overlap a bit, but I want to answer within the framework of this question. So, what is a statistical test? So, a statistical test is a situation where you set up what's called the null hypothesis. So you always set it up so that there's a null hypothesis, and for the sake of our discussions, it'll always be that some statistic has a specific value, and the alternative, we've only considered the alternative that the statistic doesn't have that value, though this is called a two-sided test because we allow for the possibility that the true value of the statistic is both greater or smaller. But there's also one-sided statistical tests, just like you can calculate the probability that something is bigger in absolute value or something is bigger just in negative value. So, but we're going to stick to two-sided tests. And so one sets up the null hypothesis that your statistic, it's typically is a mean value or a coefficient of a regression, and the hypothesis always is that it takes a specific value, and the alternative is that it doesn't. Now, what does a statistical test do? It examines whether the data you've collected supports the hypothesis of your statistical test. Okay, so looking at these last 2 bullet points, this is important. The result of a statistical test is not truth or falsity. It's not green jelly beans cause cancer. It's not cigarette smoking causes cancer. It's just that one concludes with some probability that the hypothesis cannot be rejected, or one rejects the hypothesis because the probability of it occurring is small given the data you've seen. So hypothesis testing is data driven. You start out with a hypothesis and you see to what extent the data you have statistically supports the hypothesis. Critical point. The result of a hypothesis test is not that some hypothesis is true or false. It's just that there's statistical evidence for it or there isn't. Okay, so remember when very early on in the course I gave the example of ice cream and polio, which was that it was shown that there was a correlation, a strong link between ice cream eating and amount of ice cream that was being eaten and polio. And of course we know polio is not caused by ice cream. The hidden causal factor was both in summertime people ate more ice cream, and in summertime people were around more people, so the possibility of being infected was greater. So if one was testing the hypothesis ice cream causes polio, one would see that if one set it up, probably, I don't have the actual data, you would not reject the hypothesis that ice cream causes polio. The statistical evidence supports the hypothesis, but you see it's most certainly not a fact. On the other hand, we also spent some time discussing whether, the data of whether smoking was related to cancer, and we showed, in fact, that there was strong statistical evidence that people who smoked were more likely to get, cancer. Now again, the results did not prove that smoking caused evidence. It provided evidence for the hypothesis. And then, of course, further testing shows, in fact, that smoking is a cause of cancer, and therefore one shouldn't smoke unless you don't mind getting cancer. So one very important bottom line is that statistical testing is not causal reasoning. Statistical tests do not provide a cause and effect link. Okay, so this is a really important takeaway. When you're working with this stuff in the real world, this is an important thing to understand. And with this alone, I think one can, sort of intelligently sneer when somebody tells you a study showed eating beetroots increases your hand size by 20% or whatever. I think the famous example is chocolate, where there's about an equal amount of studies showing chocolate is good for you and chocolate is bad for you. That's also kind of related to the green jelly beans. If you give enough tests, you can find anything you want. Excuse me, have a second. I just need to clean my glasses. And as long as I'm doing that, I will have a sip of coffee. Let's go. Are there any questions on what I've just said? Anyone have any thoughts? Is this hopefully pretty clear? Okay, because now we come to quiz 1. We'll get a chance. So our first quiz, and as always, just run the replies in the chat, and I'll keep track of them and let you know what the results are. So recall we had data on smokers and non-smokers with cancer, and the chi-squared test rejected the hypothesis that smokers and non-smokers with cancer were drawn from the same population. That is, the data seemed to indicate that the people who smoked had higher incidence of cancer. So which of the following statements is correct? The chi-squared test shows smoking causes cancer. The chi-squared test provides evidence for the hypothesis that cancer and smoking are linked. 3, the chi-squared test provides no evidence for the hypothesis that cancer and smoking are linked. The polls are now open. I think in light of, I have one answer for number 2. I have 2 for 2. 3 for 2. 4 for 2. All right. Everyone seems to agree. 2. Anyone else want to weigh in? All right. The correct answer is, in fact, 2. The chi-squared test didn't prove, as I said, smoking caused cancer. It provided evidence that if you smoked, you were going to have a greater chance of cancer. And it did provide evidence because it did say that the populations of smokers and non-smokers seem to have different ratios of cancer, but it most certainly didn't show that smoking caused cancer. Okay, questions 2 and 3. So that's kind of my broad take on what a statistical test is. You always set up a hypothesis and you always test the null hypothesis. Okay, and then if the data supports it at a certain level, and more on this later, you accept the hypothesis, but the hypothesis is not a fact, and if there isn't, you reject it. And rejecting the hypothesis doesn't mean the hypothesis is false. It just means you have no evidence to support it. Okay, so question 2 and 3 is, what is statistical significance and what does a p-value represent? Now, I'd like to stick to, at least for the start, linear models, because A, it's the most important application for us of statistical testing, and second of all, it's a little confusing. So with when you run a linear model, you always get the output, which also includes p-values. Now, what is happening is that you are our program is testing the hypothesis that the true value of the coefficient is 0. For every coefficient, whether it's 1, 2, 100, or 500, it's going to individually test the hypothesis that the true value of the coefficient. And of course, the data is going to give you the evidence by seeing how far the coefficient you get is actually from 0, suitably normalized for the sample size and suitably normalized for the, the variation in the data. So with linear models, the hypothesis is the true value is 0, and we've calculated a value, we've calculated the coefficient, and we wondered to what extent the value we're calculating could just be due to noise and the real value is 0. Okay, so just because it's important for us, remember what, when you do these linear models, for the statistics to be valid, you can do a linear model. The first thing I said is making this model, finding the A and B that best make y equal ax plus b, is a mathematical thing. But to have these, p-values make any sense, there's a hypothesis. And the hypothesis is that the true values, that the yi you are observing are the true values axi plus b plus some noise. When the noise is Gaussian, that means normal. And in fact, that not only that, the noise from one place to the other is independent of each other. So IID, independent, identically distributed noise. So at each point, you're not observing necessarily the true value, but you're observing the true value with noise, and the variance of this noise is going to be independent of which point you're at, and the mean, in fact, is 0. That's what noise should be. So, even if your true value is 0, there's some very, very small chance, that you'll get a value of 100 just due to the noise. So that's the hypothesis of the linear model. And this hypothesis is very important. And by the way, just as an aside, bullet point 2 is worth noting. In classical statistics, essentially there's always some sort of hypothesis that the underlying distribution, the non-deterministic aspect of your problem, is going to be that of an underlying normal distribution. And as I said before, for the linear model, the assumptions are that the residues, these eta i's, the difference between what you observe, you see, you're going to predict axi plus b, you're going to observe axi plus b plus eta I, so the noise. The difference is that they're IID and normal, and so the idea is what you're observing is that the true coefficient is something, but you're observing that true coefficient plus some noise, and the noise is random. So the true value is here, it could get over here, it could be over there. There's some chance it'll be way out there, and you want to see based on what you observe versus what you expect, and the hypothesis is you expect 0. Does this make sense? So the statistical significant means that one is likely to see data, the data you have, given the hypothesis is true. So, and this is a very important point. The statistical test measures the probability of observing the data you have, given that your underlying hypothesis is true. we'll talk more about that later. So if you see data, so if you expect a value of 0 and you see a value close to 0, suitably normalize, because remember, you have to take into account how much variation you're seeing, how big the noise is, if you will. So if you see data close in a statistical sense, you accept the hypothesis. Similarly, you reject the hypothesis if you see data if your data is very unlikely to have occurred given your hypothesis. And that's sort of, I think, the key thing. Let me stop for half a second. Are there any questions? And I think, the green jelly beans, which for me was very much fun to do, is a good idea. If you keep that in mind, this will make, I think, more sense, because you'll see, you'll be able to believe the idea that what you're seeing is not reality, but just reality with some probability. Okay. So here's sort of what sum it up for hypothesis testing in linear models. The hypothesis for linear model is that the coefficients are actually 0. Now, there's a different hypothesis and a different test value for every coefficient. Okay, so a p-value of 0.05 means we reject the hypothesis. That means if you, okay, so sometimes they're p-values, they're really t-values, and I'll discuss the difference between p and t. Is a p-value means you've got something from a normal distribution. A t-value means you've got something from a sample of a normal distribution. And in practice, the difference is only significant if the sample size is small. I think realistically, somewhere around below 5, it's very critical difference. Somewhere north of 10, it just shows up that the difference is so little, it's not worth bothering with. So you make the hypothesis that the coefficient is 0. You test, the output gives you the value of the test. It tells you the probability of observing that coefficient of that size given that the true value of the coefficient is 0. If the p-value is less than 0.05, that's typically where we reject the hypothesis. So if there's less than a 5% chance of observing a coefficient this big, if the true value is 0, we reject the hypothesis that the true value is 0, which means that it is a non-zero effect, which means we will include it in the model. So the funny little twist for linear models is, in some sense, you want to reject the hypothesis. If you reject the hypothesis, it means you found something that's useful. Okay, but if the p-value is bigger than 0.05, that means you accept the hypothesis that the true value is 0. Now, does this mean that you can't use that? No, but it means that in all probability, with a high probability, this is not, the input is not something that affects your output, and that using it is just going to confuse the issue. Okay. Quiz 2. True or false? If a statistical test for a coefficient of a linear model says the probability of observing a coefficient that large is greater than 5%, this means the coefficient is really 0. That on the nose and with moral certainty is 0. And again, I think from the way I've set it up, it's pretty clear. And you should use chat. So true or false? If the probability is greater than 5% that the coefficient is 0, does that mean it is 0? Of course, what this would mean in a standard model building exercise, you would remove that coefficient from the linear model. You would remove that variable from the linear model, because you accept the hypothesis that the true value of the coefficient is 0. Okay, but true or false? If you guess, you have a 50% chance of being right. All right. I want to have a little bit more. I'm getting 2 true. have one false. I have 3 true and 1 false. I need at least one more participant before I'm going to close the poll, so somebody has to. Remember, you only get participation points for answering. There is no penalty for a wrong answer, because I think sometimes thinking these things out is more important than getting them right. Oops. All right, we have 3 to 1 true. So maybe I didn't make it clear enough, but the correct answer as far as I'm concerned is definitely false. If a statistical test for a coefficient says the probability of getting that coefficient is greater than 5%, what that means is that you do not reject the hypothesis that the true value of the coefficient is 0. Always with statistical tests, true, false, or indifferent, it doesn't tell you reality. It doesn't mean that the true coefficient is 0. It means it's likely or highly likely, depending on it, exactly what the p-value is, that the true coefficient is 0. So for example, if you have a p-value of 5%, it means there's a 5% chance. If the p-value is 5.05 on the nose, it means there's a 5% chance of seeing a coefficient this large if the true value is 0. Now, from a point of view of statistical testing, this means we will take the coefficient out of the model. It does not mean that the true coefficient is 0. It just means we have no evidence that it isn't 0. Okay? Now, just think about it. If somebody told you you want to bet on that, and they said there's a 5% chance you're right, you probably don't want to take the bet, not if it's an even up bet. However, if there's a 5% chance that if you go down this road, you're going to get robbed, you probably think that's too much and I don't want to take that chance. So with statistical testing, you're being very strict, but it doesn't mean that it is really 0. It just means there's no evidence. The evidence supports the hypothesis. Okay? So putting a name to statistical significance, p-values. So as I said, these p-values, and I think actually in R they actually calculate t-values because they do count the sample size, but this is a reasonable confusion to make. T-value, p-value is that we're just calculating some odds of something, and because we want to be very strict, we throw out the coefficient if there's any sort of a reasonable chance that it might be 0. So that's why you reject the hypothesis if the true value is 5%, but that doesn't mean it really is. So in the linear model, our probability distributions are normal, and a p-value is something related specifically to a normal distribution. It is the probability of observing a data point that large or larger. So or that smaller if the values are negative. And again, this assumes that the underlying data is normal. Now, I'm getting a little ahead of myself, but a lot of times in the real world, data is not normal. It depends on the kind of data. Okay, so if a normal distribution has mean 0 and standard deviation 1, this is sometimes called a z-score or a z-value. And a lot of times you'll just normalize your data using by scaling it to remove the mean and dividing by the standard deviation. This will give you a process with mean 0 and standard deviation 1. So typically, when you talk about, the 95% confidence interval, excuse me, being 1.96, what this means is if you have a normal distribution of mean 0 and standard deviation 1, 95% of the data is between negative 1.96 and 1.96. Or in other words, there's a 95% chance that your z-score, the value of that you're going to get, is between negative 1.96 and positive 1.96. This doesn't mean that a value of 2.5 is impossible. It just means it's unlikely. So as I said, that when you compare z-scores to t-scores, the difference is that a t-score assumes that in fact you've only had a sample population, and so you only use the sample standard deviation and not the population. Remember that when you do statistics, when you take the standard deviation, instead of dividing by n, you divide by n minus 1 to reflect the smaller degrees of freedom, to reflect the fact that the mean has already been calculated. So they're pretty simple, and you can see, you know, from 1/2 to 1/3, that's a pretty big difference. But from 1/10 to 1/11, you're already talking about a reasonably small number. So that's why once you get a bad, you know, 10 or 12, the z-scores are very normal. The z-scores are a very good approximation for the t-scores. And the t-values are very similar to the p-values. Okay. So let me just summarize, and then I'll ask for questions. When one computes, when one computes a linear model, one is calculating from the test one calculates coefficients, and then one calculates usually a t-score, but it could be called a z-score or a p-score. It's a confusion, as I said, I don't think is very serious. One calculates the value of the probability that that coefficient is, you'd see a value, the coefficient that you've observed, given that the true value is 0. The probability you're observing is the probability of seeing that value if the true value is 0. Typically, we use a 95% confidence interval, which means we reject the hypothesis if our calculated value is less than 5%, which means there's less than a 5% chance of observing that value if the true value, I don't know if this is obscure for you or not, was 0. So if we get a p-value of less than 0.05, we reject the null hypothesis and accept the alternative that the true coefficient value of the coefficient is not 0, and we keep it in the model. Okay, that means that there is statistically, we've observed a connection between the variable and the output. I think I've said most of this, but let me just go over it. So the difference between t-distributions and the normal distribution is that the t-distribution is based on the assumption that you're sampling from a normal distribution, but you don't have any sort of in the limit issue. You're very much taking into account how many samples you have. So there is no such thing really as the t-distribution. There's a t-distribution based on the number of degrees of freedom, and the degrees of freedom is n minus 1 where there are sample sizes n. So if your sample size was 5, you would have 4 degrees of freedom. If your sample size is 100, you have 99 degrees of freedom. At that point, you might as well use a z-score, which is why you only see values of t-scores for small values of the degrees of freedom. And so if I keep saying that, we almost never see distributions with, you know, small degrees of freedom. What is its point? So the main point in modern usage of the t-test is to check and see if when you have two samples, they have the same mean. And so, you know, examples of that might be, you might have two stocks. You want to test whether they both have about the same average value. You give a drug to one group and you give the different drug or a placebo to another group. You see what percentage of the people are cured. You want to test to see if the difference of the means is statistically significant. That would say giving the drug had, you know, a real effect. So the t-test is mainly used, t-statistics are mainly used for looking at whether you have, when you have a sample population or two populations, whether the means are different. So let me just clarify that point. Let's say I have a sample and I want to know if it has non-zero mean. Right? The t-test will tell you that. You calculate the t-statistic, and depending on your level of significance, you either accept or reject the hypothesis. So for example, if you want to test the hypothesis is that the true value of the mean is non-zero, and this is something, for example, that's very important in classical financial time series, one will compute the t-statistic, which just means computing like a z-score, but using the degrees of freedom, n minus 1 instead of n, and then you have to know what the t-value is for that number of degrees of freedom, and you accept the hypothesis of that the true mean is 0 if the value is less than the appropriate t-value. So I certainly don't know, and there's no reason to know what the values of t-value are. So, excuse me. But let's just assume, for the sake of argument, that at, let's say, for given degrees of freedom, at a, let's make it different, at a 90% confidence interval, also a 10% level, the value is 2.1. So what would you do? You would say, well, with my hypothesis would be the true value is of the mean is 0. You would calculate the t-score of your sample, which will depend on the standard deviation of your sample and the sample size. If that t-score is bigger than 2.1 at the 10% level of significance, you will reject the hypothesis that the true mean is 0. If the t-score is less than 2.1, you would then accept the hypothesis that the true value of the mean is 0. So true value of a mean is 0 is kind of, I think it's pretty clear that to see how you can go from that to how do I check if I have two samples, if they have the same mean. You're going to be interested in seeing if the mean value of the differences is 0 or not. And that's why a t-test comes in. So you can either choose it to test whether a sample has mean 0 or whether two samples have the same mean. Okay, so okay, before I do this, we're digesting a lot of material, but the only thing I can say is hang in there. If you think about it a bit, it'll make sense, and hopefully this is, I think, the third time we've talked about it, so hopefully it's starting to sink in by now. Having said that, any questions now about t-scores, t-tests, t-values, p-values, hypothesis testing for linear models? All right, I'm hoping this is sinking in. Moving on. So the next question is, what are the different arguments and their values on which we accept, reject the null alternative hypothesis? Discuss all possible cases. So one sets up the level of significance. One of the most important figures in statistics is a man named Fisher, and he was the one who first invented these tests, and he specifically talked about 95 and 99% significance. So by custom, going back to Fisher, most of the time we use a 95% level of significance, which means we accept the null hypothesis as long as there's at least a 5% chance that the hypothesis is true. So we set up our null hypothesis, which is that our statistic takes a specific value. The mean of this distribution is 0. The mean of this distribution is 10. This particular coefficient of the linear model is 0. Whatever it is, you set it up, and one has to pick the level of significance, and one does this before. It's really unacceptable to go and look and say, well, I got a p-value of 8, so I'm going to use a 10% level of significance. I got a p-value of 0.03, so I'm going to use a 4% level of significance. You do this become ahead of time. And unless you have good reason not to, I would suggest using 95%. It's just standard. No one's going to argue with it. Okay, so you set up the hypothesis. You calculate the probability that you would observe the data you have under this hypothesis. As long as there's a 5% or greater chance that you would observe data in this range, you accept the hypothesis. Okay, the point of this is that you want to have very little chance that you're going to reject the hypothesis if it is true. Okay, so let me repeat that because it's important. The point of a statistical test with such a low value for the p or a high value for the confidence interval is one wants to leave little chance that you're going to reject the hypothesis as if it is true. So with a 95% confidence interval, there's only a 5% chance you're going to reject the hypothesis if it's true. Okay, and as I say, another way to put this is one calculates the 95% confidence interval for the hypothesis. So if your hypothesis is that the coefficient of this linear model is 0, you calculate the 95% confidence interval, right? And that means that 95% of the time, you're going to observe a coefficient in this interval around 0 if the true value is 0. And one accepts the hypothesis that the value you've actually observed lies in this. If you're 95% confident, the 95% confidence interval means there's only a 5% chance that you'll be outside of it. Again, as I said, this confidence interval means 95% of the time one will observe a value in this interval, given that the hypothesis is true and the correct values are normally distributed. Okay, true or false, if one uses a 95 confidence interval for hypothesis tests, there is less chance of rejecting the hypothesis if it is true than if one uses a 99% confidence interval. So what I'm asking is it with a 95% interval or a 99% confidence interval be more likely to accept the hypothesis if it's true? And keep in mind, and this is not trying to trick you, this means that 95% confidence interval means that 95% of the time you'll get a value in that range. A 99% confidence interval means 99% of the time you're going to get a value in that range. All right? So, true or false? A 95% confidence interval is less likely to reject the hypothesis, or a 99% interval is that would mean true. If you think it's a 99% confidence interval is less likely to reject the hypothesis, then that's the then it's false. While you think about it, I will have more coffee. I consider myself a good traveler. I, embrace the qualities of wherever I go. But the one thing I typically miss no matter where I go is my coffee. I like my coffee. Okay, I have one of false. Okay, let's just think about this for a second. What does a 95% confidence interval mean? It means 95% of the time you're going to get an answer in that range if your hypothesis is correct. Okay? The 99% confidence interval is larger. It means 99% of the time you're going to get a value in that range if the hypothesis is correct. So if you think about it, so that means 4% of the time it's going to be in this interval, but not in this interval. So what happens if you get a p-value of 0.03? That means you're 97. You're in the 0.03 is outside of the 95% confidence interval. Okay? So you're going to reject it. On the other hand, it's in the 99% confidence interval, because it means, if there's a 3% chance, you're in the 99% of the time interval, so you would accept it here. So this means that there are times if it's in the 95% confidence interval, it's in the 99% confidence interval. However, there are times when you're going to get an answer in the 99% confidence interval, but it's not in the 95% chance interval. In those cases, you're going to accept the hypothesis with the 99%. You're going to reject it with the 95%. So this means that, in fact, since there's going to be times when you're going to accept with 99 and reject with 95, there's going to be times when this one is going to say we accept the hypothesis, but this one will say we won't. Okay? So is there a less chance of rejecting the hypothesis? No, there's a greater chance of rejecting the hypothesis, because if you have those p-values between 5 and 1%, we're going to reject it here, but we're going to accept it here. Okay, so this is false. If one uses the 95% confidence interval, there is a greater chance of rejecting the hypothesis if it is, if it is true, than if one uses a 99% confidence interval. Okay, so important tail, keep in mind. I mean, if you think about it in terms of confidence intervals, you say, I'm going to accept it if it lies in the interval. Here's 95, here's 99. I forget, honestly, I don't remember. I think it's 1.96 is 95, and I don't remember what the 99% confidence interval is. I think we can, let's just check it. 99%, oops, 99% confidence interval z-score. See, it knows this. 2.576. So if you had a z-score of 1.96 or less, you would accept the 95% confidence interval. But if you have a z-score of 2.576, you would accept it under the 99% confidence interval, but you would reject it under the 95% confidence interval. All right? And by the way, I'm going to end this with a chart so you can see this. So statistical testing, you set up a hypothesis that you assume is true, and you focus on a criteria that makes it unlikely we will reject the hypothesis if the hypothesis is true. There's some probability that we will reject the hypothesis based on our test, even though it's true. This is the type 1 error. This is the p-values or the t-values we've been talking about, and sometimes you see this called alpha. This is type 1 error. So the type 1 error is the probability that you will reject the hypothesis even though it's true. I'm going to skip ahead from the slide, but the opposite case can happen too. You can accept the hypothesis even though it's false. That's the other case that we need to talk about. So what if the hypothesis is false? Well, one of two things could happen. Our hypothesis test can correctly say it's false, which is good, or we can accept the hypothesis even though it's wrong. In the case of the linear model, it would mean that we accept the hypothesis that the coefficient is 0, even though in fact it's not. Can this happen? Yes. It can happen due to random luck, that our observed values for our coefficient will be small, even though the actual value is non-zero. So if we get a small value, the coefficient, that would be evidence for the hypothesis that the coefficient is really 0. But if the coefficient is actually non-zero but really small, it could easily be the case that the 95% confidence interval will include the value we calculate, even though it's a non-zero but small effect. So type 2 error is type 2 error is when you accept the hypothesis even though it's wrong. So the point of the jelly bean experiment was about 5% of the time our data will reject a true hypothesis. In this case, we saw that in about 1 in 20 tests, we would reject the hypothesis that the coefficient is of the 0, even though it truly was. We were just using random noise. So we saw cases where we were rejecting the hypothesis. And the opposite can clearly happen too. We can accept the hypothesis even though it's false, and that's type 2 error. Okay, so type 2 error is sometimes called the power of the test. So the power of the test is the ability of the test to reject the hypothesis. The power of the test is sort of, well, informally, the power of the test is the ability of the test to reject a hypothesis if it's false. Type 2 error is real and important, but it's more complicated. One focuses on type 1 error because we're only interested in a statistical link, not a causal link. That makes it fair. Because if we have type 2 error, what does that mean? It means we've said our hypothesis, we believe our hypothesis is true. Our data provides statistical evidence for our hypothesis. But if in reality the hypothesis is false, We didn't claim it was true. If we're good statisticians, we just claim the evidence supports it. And what do? We go to scientists and say, we have evidence the hypothesis is true. Now do science. Find a causal model. Duplicate and replicate and find a causal model that explains this. Or say it's wrong. So for example, if you were looking at polio and ice cream, the data would support the hypothesis that there is a connection. You would have made a type 2 error. Now again, what happened? Scientists came along and said, well, we don't really see any reason why ice cream should be related. And then they went and did some little thinking and discovered, well, the point is that people eat ice cream in the summer. So the fact that the type 2 error was made was less significant. So important takeaway, statistical evidence should not be confused with scientific proof. And every time you read, study concludes chocolate causes cancer, study concludes chocolate doesn't cause cancer, study concludes organic food will make you live to 200 years, study concludes eating green jelly beans will give you acne. These are all wrong because all they've done is at best, if they did their study well and they didn't lie or cheat with how they went about it, they provided statistical evidence for the hypothesis. They have not done science. Okay? So by saying the data provides statistical evidence for the hypothesis, we mean we can't eliminate type 2 error. That's up to the scientists to go now and do a cause and effect. Now, incidentally, in the case of finance, what this means is something different. It means it's up to the people who trade to, go and see if you can make money with the trade. But in general, the statistician is not providing a cause and effect model, and the cause and effect model will tell you whether or not you had type 2 error. Okay. It is the nature of the moral of the story. It is the nature of hypothesis testing that as one decreases the probability of type 1 error, one is almost certainly increasing the probability of type 2 error. So this is some version of the there is no free lunch. Okay. How can you deal with this? Well, if in some cases where you can calculate power of tests, you can see formulas, but in general it's clear that as you increasing sample size decreases the probability of type 2 error. Now, incidentally, we've seen evidence of that in our work. You may remember that when I gave you an example of the chi-squared distribution, and I drew from two coins with different distributions of heads and tails, and the chi-squared test could not distinguish them. I think one was a 50-50 kind and one was a 45-55. And when I took samples of size 100, they couldn't distinguish them. However, you may recall I then said let's take a larger sample size, and when I increased the sample size to I think 10,000, but whatever it was, larger, now all of a sudden the difference became statistically significant. And how important this is going to depend on your case. So this is a real world thing, and how bad is type 2 error? How much do you care about this? In some senses, really, you can turn on his head and say, how much do you care about if you reject the hypothesis even though it's true, the type 1 error? So for example, if you consider a test for credit card fraud, you could probably get a test that eliminates all the cases of fraud. But to do so will probably flag a bunch of false positive, which is to say you would get a lot of cases where there isn't fraud, but the model showed there was fraud. So you can make it so that that's true, but in that case you probably wouldn't. You don't want to be calling your credit card customers twice a day and asking them, did you really do this? They're going to get tired of it. It's probably, as a business decision, more sensible to accept a small amount of fraud, i.e. have your hypothesis be there is no fraud and have a 95 or 99% confidence interval than to have a wider, a smaller confidence interval and just be absolutely certain that anything you call is fraud and you've captured all the fraud. So sometimes type 1 error is called alpha and sometimes type 2 error is called beta. And here is the long promise cartoon. So we have research and reality. So reality is what, now this is the hypothesis. So if the null hypothesis is true, if that's what your research says, and the reality is this is good. Now, if you're 95% accurate, if you're in a 95% confidence interval time, this means 95% of the time, if the null hypothesis is true, your research is going to say that, and 5% of the time, you're going to get type 1 error, and you're going to say the alternative hypothesis is true. Okay, so if your level of significance is alpha, you make a mistake alpha percent of the time. If you have a 99% confidence interval, only 1% of the time will you reject the hypothesis, the null hypothesis, even though it's true. 99% of the time, when you accept the hypothesis, it's true. However, alpha and beta are the different kinds of error, and when you make alpha really big, it makes beta bigger too. For a given sample size, it does. So if the null hypothesis is true, is what your research says, but in fact, the alternative hypothesis is true, you've made an error. It's type 2 error of beta. You've accepted the null hypothesis, even though in fact it's false. Okay. On the other hand, if your research says the alternative hypothesis is true, and in fact the alternative hypothesis is true, you're going to be accurate, to 1 minus beta. So this is why I said, power informally is beta, but really the accuracy is 1 minus the power. All right. Okay, so the last two questions is what is type 1 error and how can we compare two means with t-test? So I think we've discussed what is type 1 error. That's when you reject the hypothesis even though it's true. You set up your statistical test, you have the null hypothesis, and your data says we reject the null hypothesis, or more formally, we don't have evidence to accept the null hypothesis even though in fact it's true. And the last question was how can we pair two means with a t-test? Okay, so I think I've gone over this. Type 1 error is when we incorrectly reject it. It's controlled by the level of significance. It's called alpha. We construct a 1 minus alpha percent confidence interval for hypothesis and reject the hypothesis when our value is outside this. So if alpha is 0.05, we construct a 95% confidence interval. Where 95%, there's only a 5% chance that we reject our hypothesis if it's true, because we accept any values in the 95% confidence interval. If alpha equals 0.01, we have a 1 minus 0.01, a 99% confidence interval. We reject our hypothesis if our value falls outside of this 99% confidence interval. There's only a 1% chance we're going to do that. There's only a 1% chance that we will reject the hypothesis if it's true. This doesn't have to do, it's the exact opposite of type 2 error, where you accept the hypothesis even though it's false. So type 2, we incorrectly accept the hypothesis. This is called beta, or the power of the test. I don't know why that starts there, but it can be estimated. It's a more advanced topic. We will not be discussing actual formulas. And it's less significant in the sense that type 2 error, if in any kind of real setting, will be empirically dealt with. Science will tell you, or your trades will say, well, you said this model works, but we're losing money, you're wrong. So how do you use the t-test? This is this discussion, and we'll have more in the flights. How do we test the hypothesis that two samples are drawn from populations with the same mean? As I say, I'll have more details in the next presentation, but our hypothesis would be that we have two populations and they have the same mean. So we need to find the probability that we'll observe a difference between the two means that large, given the sample size. And again, this is under the assumption we're drawn from a normal population. What happened to that slide? I'm sorry, some slide has now gone MIA. Let me just go to the R code for a second. I want to see what happened. I had gone to the trouble to write down the formula. uh, but I lost my mouse in Denmark, and when I use the keypad, I do lots of bad things, which is why I normally use a mouse, and I must have lost that data. But the moral of this, you can look this up if you just Google search t-test for difference of means. Wikipedia will be your primary source, and you can find the formula there. But the formula is less important for two reasons. Firstly, you don't use it in practice. Secondly, in R automatically distinguishes all the important facts and just uses the correct t-test. But the important point is that as the sample size increases, the test becomes more and more accurate. Okay, so to summarize, this is my answers. This is how I understand classical statistics. It's important when you go through life and you're working with data to understand in many cases the hypothesis of normality will be violated. How serious this is will depend upon the situation, and in two important ways. It could be less or more important depending on how important a truly accurate estimate is, and it could be more or less important depending upon the result. So just to give you an example, if you're testing for cancer, you're way more concerned about having cancer and telling somebody they don't have cancer when they do, than telling somebody you have cancer, we need to do more testing. So how important this is depends on the actual situation. And then I write, this is particularly true for data involving humans, finance, psychology. The hypothesis of normality is violated. I didn't want to put it to paper, but my statement, which I don't know any counterexample of, is that any data involving human beings will violate the normal hypothesis. And it will violate it in the sense that unusual events are way more likely. Human beings tend to go overboard. So what this means is in finance, when markets go down, they go down way too much, way too fast, and way too often. Human beings have overly strong reactions more than they should. But it's particularly true. You'll find very few instances in which data involving I don't know of a single instance of data involving human beings in which the data is normally distributed. If anyone has one, I'd be delighted to see it. So what is this going to mean? That means that normal distributions have the tightest confidence intervals. You may remember that early on we discussed confidence intervals, and there was Markov's theorem, which said that you could always find a certain percentage of the data within so many standard deviations, but it was significantly worse than for normal distributions. And it's a theorem, it's a fact that unless you're doing something stupid, but any kind of normal continuous distribution, the standard normal distribution is going to have the tightest, which means your estimate is going to be the closest. So to the extent in which your data is not actually normal distributed, means your confidence intervals that the R or any other program are going to give you is too small. It's going to overstate the certainty. Okay, so here's an example. I did take a model and I gave an estimate, the standard error, the t-value, and the probability. So for the intercept, it said the value is 1.17. It gave you a standard error of 0.2057. This gave you a t-value of essentially 0. Okay, so for the intercept, we got a value, and we calculate from, you see, and it uses t-value, not p-value. It calculates that the probability of getting a value this big or bigger is essentially 0. So true or false? The intercept is non-zero. There is essentially 0 probability that the intercept is 0. The x coefficient, while small, is non-zero. Oh, I'm sorry, this is just printed on 2 lines. This next, oops, this x and so on is just the values for the coefficient of the term x. It was a regression on y on x. Okay, the x coefficient, while small, is non-zero. There's a 15% chance of observing a coefficient this large if the true value of the coefficient is minus 0.3. 5, the statistically justified model would just include the intercept. And I think rather than doing this, I'd just like to go over all these answers one by one. So for the first one, the intercept is non-zero. Well, that's certainly true. It's giving you the estimate intercept. The value is 1.1178. Let me see if I can just duplicate that. Okay, let's switch between this. At least here you can see it clearly. It showed up better as 2 lines. The intercept is oops. Let me just make it larger so you can see it. Tools, global options, appearance, font size, 18. Okay. Okay, so hopefully you can now all see this. And I ran a regression and I got the intercept was 1.178. The standard error was 0.2057. The t-value is 5.433. That's really, really large. And it says the probability of observing a value this large in the t-value, given that the true value is 0, well, is basically 0. It's 7 zeros and a 4. The x-intercept calculated a value of minus 0.3. It also had a standard error of 0.2174, but the t-value, because this is so much smaller than this, is negative 1.43, and you have a 15.5% chance of observing a value of that, or in the range of negative 1.43 to 1.43. Okay, so the intercept is non-zero. Yes, the intercept is 1.17. There is essentially a 0 probability that the intercept is 0. This is also true. The probability of getting a value this large is 0.000604, so essentially 0. Okay, so regardless of how the data is distributed, this intercept is going to be statistically valid. The x coefficient, while small, is non-zero. That's also true. The x coefficient, we estimated at negative 0.3112, or negative 0.3. There's a 15% chance of observing a coefficient this large if the true value of the coefficient is minus 0.3. False. There's a 15% chance of observing a coefficient this large if the true value of the coefficient is 0. Right? This is calculating the probability of observing this value if the true value is 0. So, I mean, it would be an excellent chance of observing a value of this if that was the true value. So what this is saying is that there's a reasonable chance that you could see this value, 15% chance you're going to see this value, even though the true value is 0. So what would this mean? In the model, you would eliminate this variable, or you would be inclined to eliminate this variable. The statistically justified model would include just the intercept. That is true. As I was saying, since there's a 15% chance that you would observe this value, and we're using a 5% level of significance, you would accept the hypothesis that the true value of this coefficient is 0 and leave it out of the model. All right. That is what I have to say about statistical testing. I hope I've fully answered the questions. I hope I've not over-answered them, but you know, I think it's better to over-answer them than under-estimate them. It's an important point. Any more questions about this? In case, I will finish my coffee while you think about any more questions on this. Cold, but still good. All right. I now have the last part of the class, which will be start this week. I want to start this week, at least give you a taste of what think about, and we'll finish next week, is sort of an ad hoc, and that's a good thing, analysis of the flights data set. I say that's a good thing because in the real world, you don't have data sets where everything works out hunky-dory. And this is a good example of that. But I want to show you how you might go about analyzing a data set in the wild. So we're going to talk about the flights data set. Just recall, this is the data of all the flights out of New York City in the year 213. And so when you're really going to do something, the first thing you should do is take a look at the summary. And so what are the fields? So it gives you the year, is all 2013, kind of stupid. It gives you the month, so it's just labeling them from 1 to 12. So all these statistics are not really important. It's really a categorical variable. It's just the category is month. Day? Well, from this we see the days range from 1 to 31, so it tells you the day of the month. So if you want to know what day a given flight was with some information, you can get it from day, month, and year, because those are things. Departure time. Well, one thing I'll point out is there's a lot of NAs, so we're missing the departure time for a lot of the data points. Well, I take that back a lot. I mean, for 8,000, there's over 300,000 data points, so it isn't really that many. But it's the time of the day. It ranges from minute 1 to 2400, which is, well, there's 24 hours in a day. So scheduled departure time, again, you can see it ranges from 106 to 2359. Now, in terms of how you want to deal with this, I mean, I understand that, say, 907 is not 907, but it's 9 o'clock and 7 minutes. But what this says is if you want to look at times, you're probably going to have to do some more work. I haven't done it yet, but that's it. So departure delay is different. That's how long it was in light. And those flights were basically on time. On average, half the times, well, half the flights were delayed by 2 minutes. But the mean was 12 minutes. And again, and this is interesting, the same 8250. Well, no, it's not surprising at all. For every flight that they don't know what time it left are the times that they don't know how late it was. Okay, but you can see that there's the smallest delay was a flight that left 43 minutes early. The largest is quite large. Okay, so we're going to have to deal with that at some point. Most of the flights, third quartile, so 75% of the flights left within 11 minutes of their scheduled departure time, but there was some that were hours. Arrival time is very similar. It's you know, the hour and time they arrived, and the scheduled arrival time is when they were scheduled, and the arrival delay is going to be the difference. Carrier says as a character, it's a list of all the different airlines. Flight, this is the flight number, so this is irrelevant really. Tail num is a way of identifying the plane. Okay. Origin, that's the airport they started from. So these are the New York City airports. Dest is destination. That's where the airport they went to. Airtime is how long they were in the air. Distance is how far the flight was. And then you have the hour time. It's just the time in hours. All right, so that's summary. So the first question we might ask is, do arrival delays depend on airport? Okay, so I take the point of view, we don't really care if a plane leaves late. We care if it arrives late. If if you're scheduled to leave at 10 and you leave at 10:15, but you're scheduled to arrive at 12 and you arrive at 12, you're just as happy. So I want to ask, do arrivals depend on the airport? So what are the airports? I use the unique function, and flights $origin gives me all the origins, and it turns out there's only three. Those are EWR is LaGuardia, EWR is Newark, LJA is LaGuardia, and JFK is JFK. Manish, who is listening, I believe, he may actually care about this. I suspect he flies out of New York City airports way more than most of us do. Okay, I'm going to want to look at means, but as we saw, there were some JFK most of the time. I don't think you're going to be so happy, Manish. We're going to be looking at means, but since there's NAs, we need to say ignore those. So what I'm really going to want to do is take the mean of X with NA.rm, NA.remove equals true, which means ignore the data points for which is an NA. So rather than write this out every time, depending on how charitable you want to be to me, you could say charitably, this is an example of work smart, not work hard, or you could just say I'm indolent and lazy. But I'm going to write a little function that's going to do that for me. So I'm going to say mn instead of mean is the function of X, which takes the value Y equals the mean of X with NA.remove true. So if I use this function mn, it's going to automatically remove all the NAs and calculate. Now, just a little point, this is if you're interested in function architecture, I want to point this out. In R, it always returns whatever you write on the last line. So if I write Y equals mean of X, the function will return this Y, because this Y is the last thing it sees. However, our functions can either return a value silently or verbosely. Now what this means is if I wrote mn of some data set, do I want it to just sort of calculate it, or do I want it to calculate it and return the value? By putting this Y again on the last line, what this means is if I ever just want to see the value, if I type mean of something, it's going to do it. It's going to show it. So let me just show you. Oops. It actually returned 5.5, which is the mean of 1 through 10. If I hadn't put this Y on the last line, it would not do that. It would just calculate the value and keep it. Let me just, in case it's unclear and you care, let me demonstrate that. So I have sandbox. So let me write so this is the format. I give the function name, and then I say equals function of whatever variables, and that's what it is. So, oops, I want this. So if I write mean foo equals function X, that means it's going to look for one value, and whatever you do to the function, you want it to put it inside these two parens, and just write Y equals mean of X NA.rm equals true. Now if I run this code, it'll now have that function. Now look, if I go min foo, it just says, okay, I calculated that. Now, it didn't put it out, but it did tell me what it is. If I say answer is min foo, if I now say what's answer, it gives me 5.5. Now, there are times when you want or times when you don't want to actually sort of verbosely see it, and that's what you do. But so that's the only reason for putting it on the last line, is by putting it on the last line. If, for example, I do want to calculate at the keyboard something, all I have to do is take mean of it and it'll come out. All right. There aren't many quizzes in this, but here's one. Which is true? A function returns what is called y. A function returns what is on the last line. A function only returns one value. I'm getting one answer for 2. I want more than one answer. I have 2 values, 2 for 2. I want a third answer, and then I'll keep you at 3. Okay, so we have 2 for 2 and 1 for 3. Okay, the correct answer is a function returns what is on the last line. This answer 3 is wrong, but it's a sort of a trick wrong, because a function in R will only return one object. It won't return one value. So you can return lots and lots of things. Like, let's say you want to, so for example, if I look at, go back here, there's a function called summary. And if I take the summary of 1 through 10, it returns all these things. Because if you analyze this, you would see it's created an object which has these 6 pieces of information in it. It's one object. The object is, I assume it's a vector, a numeric vector with name descriptions. But it's one numeric vector of length 6 with the column names on it. So the correct answer is it returns what is on the last line. It returns one object, not one value. Okay, so I've already loaded dplyr, which is the library that, now that you've been introduced to it, I strongly suggest you use instead of the basic R, this basic R SQL-like function. And I say this even though I really hate the fact that it returns tuples and not data frames. And remember that there was, with dplyr, there's this function group by, which takes all the values that has this value, in this group, and it squishes them to one line, and then summarize gives you all the properties for things. So I say delay is group by, I want to look at my flights data, so origin. So there were 3 origins. There was Newark, JFK, and LaGuardia. So it's going to take this data set, which is 100,000 lines, and reduce them to 3 lines. 1 for JFK, 1 for EWR, and 1 for LaGuardia. Just have a second here. Dim for dimension flights, and if I spell flights correctly, that's another very important thing. You see there's 22 columns, but there's 336,000 rows. So when I use this group by, I'm going to turn those 300 and some odd thousand rows into 3. And so I'm going to group by origin, so I'm just going to have one line for each origin, which is 3. And then I'm going to summarize delay. And this is just the syntax. There's no way around it. It's neither good nor bad. You create delay by group by, but until you use a summarize, it doesn't do anything. So I'm going to summarize delay. By departure delay is this MN, so the mean, but it's going to ignore NAs of departure delay. The arrival dot delay is the mean of the arrival delays, and average distance is going to be the mean of how long the flights were. And then it tells me that the bind RCPP was built under a different version of R. Doesn't matter. Incidentally, as I think I mentioned, and just there was a time when R was really slow and really bad for lots of things that were, used intensive CPU. Nowadays, for almost everything that isn't CPU intensive or involves a lot of computing power, the programs are calling C++ or C under the hood. RCPP is very specifically the program in R that allows R to access C++. So this means this dplyr package is calling C++ code under the hood to do this, which means these things happen very fast. And then I say, all right, I've created delay, and now let me take a look at what it is. And in fact, it's a tibble, and it has 3 rows: EWR, JFK, and LaGuardia. And for each row, it tells me the departure delay, the arrival delay, and the average distance. Okay, so according to this, I mean, you know, without doing any statistics, Newark looks the worst. Planes on average leave later, they arrive later. And average distance I put in here for reasons that will become clear probably a week from today. But in any event, you can see how incredibly useful this is. And the point is that with modern R, with C++ happening under the hood, this is very, very quick. Now, will your optimized Linux installation running some very nice SQL do it faster? Sure. However, I just want to show you, so this is 300,000 rows, and now it's going to execute the code, and it's done. So second-ish. It's very quick. It's very quick from a data analysis point of view. It's plenty quick. Okay, so it looks like Newark is the worst and JFK is the best. So I was wrong, Manish. You were smartly from there, at least 4 years ago. So let's check delay is what we think. So what I'm saying is, why is it doing that? We want to check that there's some statistical validity to this. So one thing we could do is, we've now seen we can have a linear model. Why would that be helpful? Because the linear model we could create 3 variables, namely the airports. Now, and we can create a variable with 3 values, excuse me, a categorical variable with 3 variables, the airports, and see if the airport is a statistically significant coefficient. That would provide evidence at the whatever level. We're going to check 95% always, so at the 5% level, that the airport you leave is relevant to how long your delay is. So let's check and see. Let's run a linear model. We're going to check departure based on a few things and see if we get a small p-value or not. So the model is going to be, we're going to check arrival delay as a function of origin, and data is delay. And the delay data is, remember, the data where we've just collapsed by airport. So we have just 3 rows: Newark, Kennedy, and LaGuardia. And we want to see if arrival delay is a function of where it is. And we run it, and then which takes no time, and then we run the summary, and it says, here's the call, great. All 3 residuals are 0. We spot on, and it's giving us a bun of NA. So it gives me the value, and then it just says there is that. And it says, and why is that? It says residual standard error NaN on 0 degrees of freedom. It's giving an R squared adjusted, an R squared of 1. That means we've completely explained the data. And this seems kind of funky. Why is that? Well, we had 3 equations and 3 unknowns. That's typically solvable, so we could exactly solve it. So there is no randomness in that. We can write a model. It might be wrong on the next piece of data, but on the 300,000 piece of data collapsed into 3 data points, we can exactly solve for that. There's an exact solution, so there is no good way to do it. So let's do something else. Let's say a flight is on time if the delay is less than 10 minutes, and if it's late otherwise. So we can use this if-else function. And this if-else function, you should, if you're familiar with any coding language, there's always an if-then, or an if, that's available in the language. If this property holds, do this. And you can be as simple as that, or it could be, if this property holds, is this. If this property doesn't hold, do something else. And that's the else clause, if-else. So if-else, flights.departure delay is less than 10. So if its departure delay is less than 10, we're going to give it the value 0. And if it's bigger than 10, we're going to give it value 1. So we create a new variable of flights on time dot departure. using if else, and it's going to take the value 0 if it was left less than 10 minutes late, and the value 1 if it left more than 10 minutes late. And similarly, on time arrival, if else, flights $, arrival delay less than 10:01. So this value is going to take the value 0 if the flight arrived less than 10 minutes late, and the value 1 if it arrived more than 10 minutes late. I mean, realistically, you always do things like this. I mean, what are you going to say? A flight's late if it's, more than a half a minute late. In real world, you don't care. And now we can redo delays. So we're going to do flights. Now keep in mind, see what I've done is I've created two new columns for the flights data frame. There's on-time.departure and on-time.arrival. I've created these new columns. So I can now say delay is grouped by flights in origin. I'm going to do the same thing. I'm going to squish by 3 lines. But now for summarize, I'm going to summarize delay by departure delay is the mean of departure delay. Arrival delay is the mean of, so I'm still going to keep track of that. Now I'm going to use this wonderful counting function, noon flights. It's going to tell me how many flights there were out of each airport. And departure delay count is going to be the sum of on-time departure. What does that mean? Remember, if you left on time, you got a value of 0. If you didn't leave on time, you got a value of 1. So summing all those, I'm going to get 1 for every time we're going to late. So departure delay count is going to tell me how many flights left late. Similarly, arrival delay count is going to be the sum of on-time arrival. And you do have to put these NA.rm equals true because just in case there were NAs. It's going to add 1 to the count every time a plane arrived late. And now when we do this, we see we have the same data we had before in terms of departure delay and arrival delay, but we also have information of how many flights and how many were delayed. So incidentally, looking at this, which airport had the fewest number of flights? Impromptu quiz. But I want at least 4 answers before I go on. Okay, so which airline had the smallest number of flights? You just have to look at this chart. You have departure delay, arrival delay, noon flights. That seems reasonable. Departure delay count and arrival delay count. So which airport had the fewest flights in 2013? I have 1 for LaGuardia. I have 2 for LaGuardia. I have 3 for LaGuardia. No, I just have 2 for LaGuardia. I'm looking for 2 more answers. 2 more people to answer. I'm not looking for 2 more different answers. All right, so I'm going to stop. Everyone agrees it's LaGuardia, and it is. Excuse me, I'll go back. Reading across, there were about 120,000 flights out of Newark, 111,000 out of JFK, and only 104,000 out of LaGuardia. And I just point out, this is very quick to do with dplyr, and you can see how you can get all sorts of interesting information out of your data that was perhaps not given to you in the first place. So if you're familiar with SQL, I think the syntax will look familiar. Otherwise, once you're familiar with the syntax, you can say, I know SQL, it's not hard. But we did notice that LaGuardia had about 20,000 less flights, so looking at the actual counts may not be as useful. You would expect it to have less delays just because there's less flights. So rather than looking at outright numbers, let's look at percentages. So we want to replace the outright count with the percentage, and that means you're going to use the transmute. Transmute, remember, creates a new number, but it gets rid of what you previously used. So I'm going to use arrival.delay percentage to be the count divided by the number of flights, and similarly for delays. This makes perfect sense. And now I have to convert it to a data frame because I want to give it row names. It's just easier to do this with a data frame. So I create the transmute creating arrival and departure delay percentage. I give it a data frame, I give it names, and then I just want it to 2 decimal places, so the round function, round delay dot percentage to 2, and actually 2, and you can see. So looking at this, the relevant one now appears to be that. Now all of a sudden it looks like LaGuardia really is better. It has a much lower percentage. So we can check, for example, so LaGuardia was the best. Newark just seems to be hopeless. There doesn't seem to be any evidence whatsoever that's good. So we can use a Fisher's test because now we can say count arrival and departure percent. One more try. Now we can count the percentage of flights that arrived on time, the percentage of flights that didn't arrive on time. So that's like a coin flip. On time, not on time. So it's like a coin flip. And we have it for LaGuardia, and we have it for Newark. So we can do Fisher's test. Okay. So what I do is I create a matrix to hold the data for Newark, and I just put in the values, 0.3 and 0.7. It was just easier to do it this way. And then similarly for LaGuardia, I put in the values. And then I check. This is arrival delay. See, so for Newark it was 0.3, 0.7. That's like, so it's a coin where 0.3% of the time it came up tails, meaning you arrived late. And similarly for LaGuardia. And then I can just do the Fisher's test. I bind the 2 things into a matrix, and it accepts the hypothesis. The p-value is 1. So it says according to Fisher's test they are the same. Departures will also say the same. So it says there's no statistical difference. Okay, but I'm personally not convinced yet, and I have good reason not to be. Remember I gave the example where we needed a larger sample size to see if there was a statistical difference. It may be the same here too. So let's redo the test with the actual numbers that we have from the data frame. So now I'm going to create the arrival for Newark and LaGuardia, but now I'm going to put in the first, for each of them, I'm going to put the top row, the arrival delay, and if I look at the total number of flights minus the number that arrived late, that's the number of flights that were on time. So in fact, if I do that, I will see that for for Newark there were 36,000 flights late, 84,000 flights on time. For LaGuardia there were 28,000 and change flights that were late, and 76,000 flights that were on time. And I'm asking if it looks like, if you will, if I flip this one coin 120,000 times, and I flip this other coin 104,000 times, and got this many heads and this many tails for this one, and this many heads and this many tails for a different one, do I think they're drawn from the same? And now I get a p-value of essentially 0. So we're going to reject the null hypothesis that they were drawn from the same distribution, and accept that the true hypothesis that the true odds ratio is not 1, i.e. that the percentage of on-time flights at Newark is different than the percentage of on-time flights, that's Newark, is different from the percentage of on-time flights of LaGuardia. So we see when we put in the actual data, we do not accept the statistical hypothesis that they're same, and we conclude statistically there's good evidence that if you want to arrive on time, you should leave from LaGuardia and not Newark. You're better off. So, as I say, intuitively, while the percentage differences may not be that great, we have rather large sample sizes. And what this means is that any difference we observe is more likely to be real than if we have smaller sample size. An example I give is if a guy tells you I know how to pick stocks, and he picks 2 winning stocks out of 3, it's 67% right. That's certainly better than average, but you say you only picked 3 stocks, you could have easily have gotten lucky. But if he picked 2 million winning stocks out of 3 million stocks, so if he made 3 million picks and was right 60% of 67% of the time, you're more inclined to think that this guy knows what he's doing. He's consistently able to pick it. The evidence that this is not a 50-50 game for this fellow is greater. So more formally, increasing the sample size decreases the chance of a type 2 error. Any questions? All right, I'm just going to go 1 or 2 more slides, and then we're going to call it a day, and then we'll finish this next week when we'll get into more interesting questions. So I'm going to do 1 or 2 more slides, and I'm going to just show you some of the other things we're going to talk about, but we'll really be talking about them next week. So I just, for fun, I did the same thing for departures. Though we're less concerned, again, we see that if you want to leave on time, if for some reason that's important to you, again, Newark was far worse than LaGuardia. So that's only the very first simple question. There's lots of questions. For example, I have a friend who says, I always catch the first flight. Why? They're much more likely to be on time. I'm almost never late. They leave on time because the equipment's there. It doesn't have to come from somewhere. Is he right or wrong? We're going to go through that. And we have a lot of different things. Here, I will give you a t-test example. Oh, that's where I wrote it down, but we'll discuss this next week. I have a lot of things, and we're going to eventually wind up with some cool graphs and some ideas on whether we can predict how long a flight is likely to be delayed based on what information might lead one to a good prediction. And we're going to get to see a bunch of cool graphs like this. All right, so I don't know exactly when it will be administered, but we're ready now to take the final exam, which will be a project similar to the midterm, but with more emphasis on doing a linear model and doing analysis with a linear model. All right, let's go back. And of course, as you can see from the color, we're going to get to do some more fun things with ggplot. I mean, I think, the fact that you can do a graph like this with just 2 or 3 lines of code is miraculous is way too strong a word, but it's really, really cool, and it's really, really useful. And when you're out there and somebody asks you for graphs and you produce things like this, and it didn't take you 2 days, it took you 5 minutes, it's really a wonderful thing. All right. Any further questions? All right, so next week, excuse me, I'll briefly recap what we did this week, and then we'll finish the analysis of flights and see what information we can garner and see if you can reasonably predict how late a flight is going to be, and learn, do some more examples with dplyr and ggplot. If there's no more questions, I'm going to call it a day.